Okay, so good morning everybody. This morning I will try and talk a little bit slower than I did yesterday, as I believe some people had some difficulty understanding me. So this is work package 6, the formal barriers to education. Kevin Kelly is who I am from Trinity College Dublin, for those who may not have been here yesterday. So first of all, I'd like to thank all the partners who've cooperated. Feedback here. All the cooperation from all the partners in the different work packages. And in particular Claire Marshall, my co-worker in Trinity College, who's responsible for a lot of what you see today. So in work package 6 we had the aims to examine the formal barriers to engineering education at third level. The purpose being here to try and make sure that we could have access for as many students as possible to engineering education, but we have to do this in a way that does not compromise the standards and that does not admit students who are not equipped to cope with the third level engineering program. There were 3 main phases of work that we undertook in work package 6. The first task that we began was a survey of all the partners in the project to try and understand the education system. So we designed a survey which was sent to all partners just to document how their country worked. Is it just me, or is there feedback affecting?
It is.
Okay. I'll try moving the microphones. Maybe that's better. Okay. So you can hear me breathe and talk. So we have, first of all, the survey of the different countries, as I say. We use this information then to assemble what we call the comparison framework. So one of the issues, as I said yesterday, we found in the project was that it was very difficult to make comparisons between the different countries because the structures of the education systems were different. So we tried to assemble all this information from the survey in phase 1 and to compile it in a reference document that was easy for people to go to see a direct comparison between any 2 individual partners in the project. And having completed the comparison framework, then we wish to compile the report on what the barriers were and present that. So the questionnaire was distributed to all partners, which, as I say, documented the education systems, and this was all the way from the beginning of the education system at the primary level up to later in the education system at the high school or secondary school level, including the university entry mechanisms. And we were also interested in the provision of subjects in the science, engineering and technology, or science, technology, engineering and mathematics, STEM. So the survey was a pretty extensive questionnaire. I think many of the partners were sick of us after the first few months because we kept asking for more and more information. We documented all of this information, as I said, and we used that then to inform the work that we performed in work package 6. The comparison framework, which I'll present some results from, but the full framework is available in the final report and is available on the Attract website, was to provide at a glance information. So you can, if you want to compare something or you plan to implement something maybe that you've seen in one country and you'd like to do this in another, you can see what are the differences in the education system and maybe understand what would you have to do or what would you have to change to transfer knowledge from one country to another. So it provides the context to enable the conclusions to be drawn between the different countries. We tried to keep it very visual, so there's a lot of graphs, tables. Sometimes it was unavoidable, we had to use text information, but we tried to minimize that information. The report itself then, we documented what the factors were that were restricted access. We looked at any research that we could find which looked at the impact that these barriers have on access to engineering. And finally, where we could get any data, we tried to look at this data which established any relationship between the entry mechanism or the entry barriers and the progression of the students later in the system. So what do we mean by barriers? Well, what we've said in this work package is that barriers are any factors which stand in the way of entry to engineering programs. So these can be set by the universities in the form of entrance mechanisms, they can be requirements that the professional bodies impose, or they may be barriers that result from structural conditions in the education system, or indeed from cultural or socio-economic factors in the country. Put it very simply, how are potential students prevented from studying engineering? That's really what we want to see in this work package. The main categories we identified then were the entry requirements for engineering programs, the structures within the school system. So for example, are there particular streams or tracks which students choose or have to choose, which may effectively make that decision, or the students are making the decision not to do engineering or to keep the possibility open for engineering at quite an early age, maybe before they even really know what engineering is. And then on the socioeconomic factors, one of the things that has been seen is that engineering programs in several countries appear to be less diverse in socioeconomic terms than other university programs. So typically, if you look at science and technology programs, the number of students from lower socioeconomic groups as a percentage is smaller than in other programs like arts or humanities or business. So going through these barriers then, in the high school system, this is an example of a graph from the comparison framework. It just shows in the different partners who responded to our survey here, when does the education system begin? And what we've done is we've graphed what is the full-time compulsory education and what is not necessarily compulsory education, so where there's a degree of choice or it's part-time, and then the different stages from preschool all the way through to upper secondary school. So you can see there's quite a lot of similarities in some respects. All the countries have some sort of upper secondary level education, but the duration of the system, when students start, when they have to finish, or what degree of choice they have, and the length of each of these components is different in each of the countries. So even at very high level, we see significant differences. We also see a separation in most countries between the academic and vocational branches of education, particularly at the upper secondary school or the final stages of high school. So this choice is typically made at about the age of 15, and this can impact then on the students' options at higher education. So students who've chosen a more vocational or practical path may not be eligible for academic study at the university, depending on the country. And also then any specializations that the students choose here may create further restrictions. So students who don't choose a science or technology track, or don't choose enough science or technology subjects, may not be eligible for entry to the engineering programs. So again, this can be an issue because students are making these choices explicitly at maybe age 15, but implicitly decisions are beginning to be made much younger, even 10, 11, sometimes even younger than this. So these are quite important issues. Within the high school systems then, this is a look at how the different countries have a breakdown within their systems of the academic tracks and the vocational or professional tracks and other tracks within the system. So we can see, again, quite a lot of similarity between most countries here. Ireland stands in quite stark contrast in that our vocational education is a very small percentage of our high school system. Many countries also operate a track-based system, so this is where the students choose a business track or a languages track or a science and technology track at the upper secondary level. So typically, as I say, these provide specialized education areas. Students can specialize then based on their interest and or their ability, usually with assistance from the parents and the teachers and so on. Other countries will use a more general system where there's a broader range of subjects and students have more or less a free choice. There may be some compulsory subjects, but they can choose other subjects around those. So for example, here we see in Ireland and in Finland, there's a more general education system where students have a lot of choice, and Belgium, Italy, Portugal and Sweden have a more track-based system. The gender issue is an important one for this project, and I think Carla will talk a lot about this in Work Package 7, but we've also addressed it in Work Package 6. And we see that there's very significant gender differences, not only at the university level, but also at the high school level. So girls in general are much less likely to take physical science subjects, particularly things like physics. In Ireland we have a particular problem with lots of these technology related subjects because, as lots of people know, we had a country in which the church was very important and they didn't like mixing boys and girls because we would think all sorts of strange and thoughts that they didn't like. So we have lots of schools which are all girls or all boys, and in all girls schools in particular, technology subjects quite often are not even taught, and where they are, there's quite a low uptake. So this is a significant barrier from a gender perspective. And this has led to a certain amount of research which does suggest that there is a direct causal relationship between the percentage of girls who take these subjects in high school and therefore the percentage who enter engineering and technology programs at university. Another interesting issue is when we look at the different countries, even if students want to make these choices in the different areas, what is the exposure that they get progressively through the education system? Because we know the decision is not a case of students having no idea of what they want to do and then one day they just make that decision, which is the day they have to make the decision. This decision evolves over time with the information and the environment that they have. And particularly, obviously, in engineering, we're very interested in the science, technology, engineering and maths subjects, because exposure to these and interest in these subjects will then encourage students to pursue them at the university level. So what we wanted to look at was across the different European countries, how are students introduced to these subjects? How much time do they spend studying these subjects? And this produced some quite interesting results. So this is an example for mathematics. And what we're looking at here is the age of the student from the beginning of the education system through to when they graduate high school. And we have the total number of hours exposure that the students get to particular subjects. There's some approximations here. And what we're also looking at, if we look at any individual curve here, so for example, this red line here represents Portugal. So the solid line that goes up through here in each of the cases, this represents a typical student. So if we look at the average student in the system, this is how many hours exposure to mathematics those students get in Portugal. And the bars here represent the maximum and minimum. So where there's a degree of choice to how much the student wants to do, then we see that there can be quite a wide difference between a student who chooses to maximize the amount and a student who chooses to minimize. So what we see here is not enormous differences between Ireland, Finland, Sweden. Italy is maybe a little bit lower than in practice because I think we had an interpretation issue with the information here. So it's not that Italians don't encounter mathematics until 11. It's that the structure of the syllabus, I think, means that they're not, it's not prescribed. Is that right, Anita? That students, it's up to the school to decide how much time to spend on particular subjects, I think, at this level. But this is interesting nonetheless. We see quite significant differences then between the different countries. If we look at other subjects, for example, physics, again, we see significant differences here. And if we look at chemistry, again, we see significant differences there. So some countries, if we look at Finland, for example, students are mandated. So here, if you look at the minimum amount, is quite a significant amount of exposure to chemistry through the high school system. Whereas if you compare that to, for example, Sweden or to Ireland, the maximum exposure that students get is less than the minimum possible exposure in a country like Finland. So quite significant differences. What kind of requirements do the universities themselves have then for entry? Well, is there a restriction on the number of students that are allowed to enter, or numerous clauses, as it's often referred to? In the case of these countries, yes, these countries have a limited entry and they can then select by some mechanism which students enter and which students don't. And some countries don't have this mechanism, so any student who wishes to enter an engineering program can enter the program. In the event then that the university has to choose the students who come in, what control do they have over the student selection? Well, again, here in Finland, the university has very strong control over which students enters, but in the other countries, there's a more sort of national system for allocation of these resources. The specific entry requirements then, there are no subject requirements in Italy or in Belgium. However, all students must study a core component in the high school which involves a certain amount of mathematics and a certain amount of science. Mathematics is required in all other countries, and physics and chemistry are required in most countries for entry to the engineering programs. A result of these requirements then is that there are a limited number of students who are leaving the high school system who are actually eligible to enter the university system, and that's quite a significant limitation. We can see in Ireland and in Sweden, for example, there's about 12% of students are eligible. So 88% of students leaving our system cannot enter the engineering program. And again, because of the structure of the education system, these decisions are being made at 15 or even earlier. So this is quite significant. What about the criteria themselves? Well, the exact criteria that the universities have varies in the different countries. All of the attract countries use one of the following or some combination of the following. So examinations in the high school, grades from ongoing performance or continuous assessment in the school, excuse me, or some form of university entrance examination. Grades in particular subjects are often required. So we see here the mathematics requirement across most of the countries, and as I noted on the previous slide, Italy and Belgium, which don't have a specific mathematics requirement, that's almost implicit because the students must study a certain amount of mathematics and mathematics in the high school system. And again, we see some differences here in terms of what students are required to have before entering the programs. So, the percentage of students then that are eligible to enter, I mentioned Ireland and Sweden have about 12%. We see Finland, it's closer to 20. Portugal is up at 40, and because Italy and Belgium must take everybody, technically 100% of students are eligible for entry. So we have these barriers then in place, these entry mechanisms, and we want to ask the question as to whether they actually serve the purpose they're there for. What is the purpose of the barriers? We can hypothesize maybe there's two principal purposes. One is to say this is a level of knowledge that we require, so we say it's the responsibility of the high school system to provide this knowledge and not the university system. This is one barrier, or one reason, I suppose, for the barriers. And a second reason is it's some way of identifying aptitude or capability of the students to progress in the system. So what we have tried to look for then is any correlation between achievements in the entry, or between prior achievements at the high school level related to the entry requirements and how the students subsequently perform in the university. So we have some data which I'll present from both IST in Portugal and from Trinity College in Dublin. One of the things in IST is that there was a change in the entry requirements in recent years, so there's now higher entry requirements, and what they see is that the difference between the students now at the higher entry requirements is that they on average progress much better through the system. So the entry requirements in some senses were identifying people who progressed well. It's important to note as well that in most countries there are often alternative entry routes for students into the university system. The reason for having these is to allow students from a non-traditional background, so maybe students who didn't finish high school but have some working experience, or students who have come through some other route or represent a socially disadvantaged group, for example. So those not meeting the standard requirements, typically there's some mechanism for introducing students. And the proportion can vary quite a lot. So in Italy there's almost no students coming through this kind of route, and in Sweden compared to the other countries there's a very high percentage. So different countries have to deal with quite different situations in terms of their students. The socioeconomic and cultural factors then. Engineering courses, as I've mentioned, are typically a lot less accessible to students from socioeconomic backgrounds, and this is reported in lots of surveys, most recently the Euro Student Survey last year. And it's also reflected in the data that we've seen directly from several of the attract countries. So for example, in Ireland, Sweden and Italy, engineering programs don't tend to draw from as broad a socio-economic mix as other programs in the university. In Ireland, for example, one interesting result was that the PISA scores in mathematics were very significantly, statistically significantly higher among students with high socio-economic status. So we would expect in general better academic performance from higher socioeconomic groups, but it's particularly evident in the mathematics, which is obviously quite relevant for engineering programs. Just sticking with PISA, and this is where the engineer in me comes out, and I like to have a few graphs, so Claire advised me not to have too many, so sorry Claire. But I like graphs, I'm an engineer. So we have science here, the PISA scores in science and the PISA scores in mathematics. And what these dots are representing, each dot represents one individual country, and the size of this represents the GDP per capita. And what we see really is that most of the large dots here are up at the high end of the graph, the top right of the graph, which means that countries which are achieving highly in mathematics and science at the high school level are countries which are prosperous. Now we can argue, are they achieving highly because they're prosperous? But I think it's much more likely they are prosperous because they achieve highly in these areas. And we also see there's a very strong correlation between the mathematics and sciences score in most cases. And I've identified the different project countries there. So that may be interesting for us all to reflect on and where our own countries sit and think about why that might be the case. In the text of the PISA report, they did make some very interesting observations, including one that the number of students reaching level 5 or 6 in mathematics and science, so this is a level defined as kind of a degree of excellence, if you like, in mathematics and science, is particularly important for countries wishing to create a pool of workers able to advance the frontiers of scientific and technological knowledge in the future and compete in the global economy. So in other words, it's not just the average that's important, we also need to be achieving significant performance or or significant numbers achieving the really high performance in these areas. And this is quite depressing for some countries. So my own country is down here right at the bottom. Only 5% of the students in Ireland achieve a high percentage at level 5, and only 1% achieve level 6. And this compares to, for example, Finland, of the project countries here, 16% at level 5 and 6% at level 6. And we see similar patterns in the science. Okay, so now we move on to the data we had regarding the student entry and the influence on student progression. So what we wanted to see here, as I've said earlier, was is there a relationship between the entry requirements that exist and the factors that are the success of the students in progressing through the system, and are other variables present and what influence do they have? So we have three data sets of different types that we've obtained from the different countries. I'll briefly go through them, or not so briefly maybe. We have Polito in Italy, Trinity College in Ireland, and IST in Portugal. In Trinity College and IST, we were examining the student background and the prior educational achievement before the university. And in the case of Polito, there was aptitude tests which were given to the students after entry to the university. But these are not used for assessment, they're simply for information purposes. But we were able to compare those then to the credits that the students gained during the first year. So as I've said, the students coming into Polito then, they sit these aptitude tests in three areas: mathematics, logic and comprehension. And the results are not used to grade students, they're just for, or for admission, they're used for information purposes. What we see is a very strong correlation between how the students perform in these aptitude tests and the amount of credits gained in studies. So like most European countries, Polito operates a system where the students must accumulate credits as they progress through the system, and the number of credits can vary from student to student in any particular academic year. So here we see this is the lowest achievers on the aptitude test, the bottom 10%, and we see that most of these students achieve a very low number of credits in first year, and then we have this very low percentage of those students with a low aptitude score who achieve a large number of credits. And we look at the top 10% and we see completely the opposite. So we can compare those and we get a very clear picture. There's a very strong correlation then between the aptitude of the students as measured in these tests and how well they progress in the system. In IST then, we were looking at the information that the higher education institutes of the universities, the information that they get on the new students at student entry time, and can that be used to predict performance. So the data here was from 2004-2005, looking at just over 1,200 students. And the data was analysed under a number of headings: the academic background, motivation, socioeconomic status, and other factors. Parental education was not significant, maybe slightly surprising. Household income was quite an interesting one, because students with an income below the average tended to do better in the university. And the suggested reason, I think, here was that typically these are scholarship students, so they are extra motivated to do well so that they can retain the scholarship. Female students outperform the males, so this is not that surprising. Maybe we see this in the high school system in most of the world. We also see in the university level that gender is often significant, or usually significant even. The background then revealed a significant relationship between the grades in high school and the academic achievement at university. And if I recall correctly, Carla, this was the continuous assessment of the students in the high school was most significant, not the end of school exams. Whether or not students studied physics, so not the achievement level in physics, but just the fact that they had studied physics was important, made them much more likely to succeed. Students who get their first choice program are more likely to succeed than those who don't. If students expect to do well, they tend to do well, and students who don't expect to do well don't tend to do well. And the time at which they make this decision, so those who had chosen earlier rather than later to enter the programs tended to do better than as a result. The contextual factors then was looking at things like the residential status, so did students live at home or do they live away from home, and we saw students living at home performed better. And the travel time was also significant, so students who had to spend a long time travelling didn't achieve as well. In Trinity then, we looked at some quite similar questions. We wanted to look at the entry data again and see how did that affect performance in the first year. Can we identify students who are less likely to progress to second year? So I should say here really that the system in Ireland is a little bit different in that we have a syllabus or curriculum for first year, and students must pass the entire curriculum for first year before they can progress to the second year. So it's not just a credit accumulation system as it is in many other countries. Here we were looking at a larger number of students and over a longer period of time, 2000 to 2009. What we looked at, whether students took particular subjects. Students in Ireland can choose which subjects they want to take, how well they achieved in those subjects, which engineering course that they chose in the university, whether they were male or female. We looked at whether there was a change over time. I'll come back to the CAO mark. This is used to allocate places in the university. You can think of it like a grade point average from high school. Whether students lived at home, and the output we were looking at was whether they progressed to the second year of study within one academic year. To take a typical student, a typical Irish student will take 7 subjects for their leaving cert, and they'll receive grades that look something like this. So here we have a student who's chosen mathematics, physics, Irish at the lower level, which is quite common. Most subjects can be studied at a higher or lower level, and English, French, chemistry, economics. So this is just an imaginary student. They would receive then a score or a grade point average for each of these subjects, and the best 6 subjects are combined to give them a total, and then this is used to allocate limited places. So anytime you see me talk about CAO scores, I'm referring to how we allocate the places within where there's more demand than supply. What we found was achievement in mathematics was the single biggest advantage to students, not too surprisingly. Physics and chemistry were also important, provided students achieve reasonably well. If they achieve poorly in those subjects, then they do worse than students who haven't studied those subjects previously. Interestingly, in engineering, we found that gender was not significant in Trinity. So we had a large number of students, about 20-25% female, which would compare to the university as a whole, which is about 62% female. And we found gender wasn't significant. So that's interesting, even though it is in the university as a whole. What we did, and look, I have exponentials for all the engineers, woohoo, and infinity signs, this is great. So I won't spend too long, we took the inputs, so whether they'd studied these subjects, how well they achieved, we put them together, put it into this function, and out comes a number which is a probability that the student moves to the next level. So if we looked at any individual subject, what we see is there's a negative effect for students who achieve poorly, and as their achievement starts to improve, that effect becomes positive and then saturates somewhere out here. So this is looking at one subject, the subject accounting. So somewhere in here, there's a level at which the effect goes from positive to negative. There's an achievement level. If students achieve above that, it increases their chances of progressing. If they achieve below that, it decreases their chances of progressing. So that's it takes quite a lot of space just to show one subject there, so we decided to look at another way of presenting it, and this is the same information as on the previous slide, looking at the minimum effect here, so that would correspond to this level here, that level there, up to the maximum level, which is here, and that corresponds to up there. And then this is for students who fail the subject. So somewhere in here there's a critical mark at which it crosses the 0 line, and in this case for accounting that is about 65%. And if we look then at all the subjects which are statistically significant, we see here we've got accounting, economics, building construction, chemistry, physics, mathematics having the biggest effect. And interestingly, students who choose to study Irish at the lower level, it doesn't matter how well or how badly they do, the fact they've made that choice, they tend to do slightly less well. Now, this information here tells us, in a sense, what subjects at the high school level are important in predicting how students will progress at the university level. So one of the obvious questions for us to ask then is, well, do many students, because students have the choice to study these subjects, do many students study these subjects? And if they do, how well do they achieve in these subjects? And what we find here is that this is the percentage of our students in Trinity who took these subjects, and I've highlighted the ones here which are important for engineering. So you can see in general they're not among the more popular subjects, and the divisions here between the two different colours are gender. So Trinity as a whole is 62% female, and you see that reflected in many of the subjects, but the subjects which are important for engineering also tend to be subjects which are not studied as much by females. So not alone do we have subjects which are not particularly popular, but we have these students are not being exposed to these subjects at the high school level in the same number. So this is quite important. We then have an even bigger problem, which is if we look at where this grade point average comes from, we find that certain subjects contribute more to the grade point average than others. So subjects above the line here are students who get more of their grade point average from these subjects, and subjects below the line, students get less of their grade point average from these subjects. So in some sense it indicates a difficulty or an achievement, a relative achievement compared to the students' average competence across all the subjects that they take. And again, we see the majority of subjects here that are important for engineering are the harder subjects. They're subjects that students don't achieve in as well. The one exception is building construction, but we see here only a tiny percentage, 1.5% of students study it. Also, there's very significant gender effects. So women significantly underperform in all of these subjects compared to males, whereas the opposite is true if we look at languages, for example. Typically the female students achieve relatively better than the males. So we have real problems here. Not enough girls are being exposed to these subjects, and those that aren't achieving as well. We don't know why. There's lots of reasons. Maybe it's a cultural bias, maybe it's the teaching, maybe it's the schools that they're in, because many students in Ireland are in gender segregated schools. So if we take the results then and we see, well, how can we use these results? Well, one of the things we can do is to say, let's take this typical student and try and predict what probability they have of going through the system. So I apologize for this slide, maybe there's a lot going on, but we've seen most of the parts before. This is the effect individual subjects have. This is our notional student here. And what happens is the student starts off, when we have no information about them, they have some default level of probability of progressing. So they're somewhere on this scale here, which equates to a probability here of about 0.5. So they're about 50% likely to go through, 50% not likely. And then as we start looking at their achievements in individual subjects, it moves this line here. So that's a positive effect. It moves this line to the right, which starts to move us up this curve and increases the probability here. So this student then becomes more likely to progress, and we can add in the other subjects as we go. So we can see the Irish slightly decreases their chances. Chemistry at that level is below the critical level, so it actually decreases their chances, and economics the same thing. So this student ends up having about that probability of progressing. How effective is it? Well, to answer that question, one of the things we could do is just look at some sample data here. So imagine this is 20 students, approximately 50% of whom we expect to progress and 50% we don't, and we've tried to predict every individual student. So what I've done is basically, this is a probability axis, so this is the percentage probability, or the probability that each of these students progresses, and then I've just shaded the lines to indicate these are, the dark lines are students who actually progress, the lighter lines are students who don't. So if we take some particular level here and we say, right, above that level, we would expect any student who achieves above that probability, say about 55%, will they progress? Well, we see that above that threshold level, we have 1, 2, 3, 4, 5, 6, 7 students who progressed. And we also have 2 students who are above that level who didn't progress. And similarly, down here, we've got 1, 2 students who are below that level, but nonetheless managed to go through. So we could take that data and we could represent that in the form of a table here. We had 7 students who were a true positive. That is, we predicted they would go through, and they went through. We had 9 students, that's these ones down here, who were true negatives. We predicted they wouldn't go through, and they didn't. And we had some false negatives and some false positives. Some students we predicted would go through and didn't, and some students we predicted wouldn't go through and did. So we can define a false positive rate, which is the number of false positives here plus the true negatives, and that's the denominator, and then it's the number of false positives over that. So 18% false positive rate and a true positive rate, which is the true positives over the true positives plus the false negatives, and 78% is the figure. So effectively, at that level, that threshold if you like, we have this level of false positives and this level of false negatives. We can then represent that on a graph here, which is called a receiver operating characteristic, which allows us to basically see how good are we at predicting at various false positives and various false negatives. So there's always a compromise to be made between the accuracy of our prediction and the cost of making the prediction. I won't spend too long on this, but this is just to show if we had no information, that would be this line here. And then this light green line represents using the information that I've just displayed on the previous slides. And even using the best possible information from previous research in the area, we can see there's somewhat significant differences, particularly in this lower region here. How can we use that? Well, one of the things we might do is to say, well, if we can potentially identify these students who may be at difficulty of progressing, then we can put in place some initiatives to help them. We can say we'll provide extra support, or we will do something with these students. And if we're doing that, then these students here are the students who, if we provide some special services for some students, then the students below that threshold level that we don't provide the service for, they weren't going to get through anyway. They still don't get through. And we have some students who progressed as before and some students who didn't. And here we have some students who we provide a service to now, or assistance. They got through before and now they continue to get through, but it's here. This is the students who we predicted before would have difficulties, and we're now providing a service. So this is the area we're really targeting. We're saying if we provide these assistance or service to these, maybe we can make a difference. So whatever, it's this column here, the people we expose to whatever help or initiatives we put in place. And what we can do then is we can look at various costs associated with that. So we put together a simple tool in the project, just an Excel sheet, which allowed us to model the financial implications of providing assistance. So we can look at what level of success we expect to get from our initiative. So what percentage of students who previously failed would now be expected to pass, and that's represented here. And then the percentage of the total population that we target, and we can look here then at the costs of providing that initiative, depending on how much money we save if we retain a student, how much money we lose if they fail to progress. So it allows us to make an economic decision as to whether we should put in place some particular initiative. To conclude, and I think I might actually just about be on time, on the recommendations then, the main conclusion is there's no single very simple set of recommendations that apply across all countries. What we have is some things which are in common, which I'll talk about now. But there are particular challenges due to the systems and structures in each particular country. So each of the partner countries has developed their own specific recommendations, which are in the report. But we have certain general recommendations, I suppose, we were able to extract from the report from all partners. So the aim of these changes is to try and expand the number of motivated, the number of qualified, and the number of suitable students applying for and taking up places in engineering programs in our countries. Three categories of changes recommended: those to the admission requirements, those to the education system, and then those that address the socioeconomic and cultural issues. We've also looked at how easy we think it would be to implement these, whether it's straightforward, whether it's moderately difficult or very difficult, and again they vary from country to country. General recommendations would be, in terms of admission requirements, mathematics is pretty general but should continue to be so. We see that it does predict pretty well how students perform. Physics and chemistry, again, we would recommend across the partner countries. In the educational systems, I think it's important in most countries that there's a higher level of preparation in STEM, more in some countries than others. It will be a benefit to have later tracking of the students so that students aren't being maybe forced to make these very important decisions at such a young age. And that we need to have a core content of STEM subjects for all students. It's important that all students get exposed to these. However, if we start to put in place entry requirements that we want students to have physics, or to have chemistry, or to have mathematics, it starts to shrink the number of available students. So we have to, as well as changing any admission requirements, we also need to equip more students to meet these standards in the high school system. On the socioeconomic and cultural issues then, it's important that we show the relevance of the science, technology, engineering and mathematics subjects to real life. So this is a pedagogical issue, maybe more active learning, more project-based learning, more constructivist learning maybe would be good things to see in the STEM subjects. The number of females pursuing engineering is a problem, we know this, and we think that this has to be addressed both in terms of encouraging people at the university level, but also in terms of the way our high school system works to make sure that girls are equally encouraged to pursue the engineering. So there are cultural and social issues there as well. And we do notice that in most countries we have this smaller socioeconomic diversity within the technological subjects. So that's something that needs more work to address. So I think with that, that's enough of me talking for now, but if anybody has any questions, I'd be happy to answer.